So good afternoon, everybody. I'll present you some investigation we have done on hardware compression using the IBM Power system. So Pierre and I are from the data analysis unit at ESRF, and I'd like to acknowledge the hard work that my colleagues in the TID have done, especially Antoine Roux and Benoît Roussel, who allowed us to test this system. No? Yeah, of course. So the outline of my talk is, well, I'll focus first on the bandwidth issue we are facing here at ESRF, and which is shared probably by most synchrotron sources. Then I will present you some of the evaluated system. I will focus a bit on the need for compression of scientific data before drawing some conclusion. So this slide comes from a publication we did last year, and which presents a setup we have here in production since 2015 or 16, where you have well, at that time it was a high-speed detector, which was writing using NFS over FDMA on a server using a 10 gigabit link, and the 10 gigabit link. So the data was fooling all the 10 gigabit link. And from the server, if you look at the different bandwidths we have available, so we have 120 gigabytes per second to the memory, which is large, so it's great. But if we want to save data on even high-end SSDs at that time, we couldn't afford to write and read at the same time. It would already create some traffic jams. So the only option we had was to send the data to a GPU, at that time it was 6 gigabytes per second, perform some processing there, and write the data to the GPFS. For this application, we focused on data reduction, online data reduction, but you can understand that data compression is also an interesting topic. So today, we are upgrading this kind of link from 10 gigabit per second to 100 gigabit per second. So if we keep the same server, well, we are in big trouble because you add a 0 here, but you don't add a 0 here, or here. So compression becomes mandatory. We have discussed this morning already. And so what is on the market today? So I will present you some topology of Intel Xeon servers as we have in 2019. So we have the classical 2U system, 2 sockets, interconnected with PCI Express generation 3. We have 6 memory channels per processor, and then we have 2 sockets, 4 socket system, or 8 socket system. So the more socket, the more processor you put, the more memory lanes you have, the more bandwidth to the memory you have, but the PCI Express remains the same. I was given the opportunity to test an IBM AC922 server from IBM with Power9 system. So the topology looks really similar to what we have with a 2 socket system in the Intel world. So we have 2 processors. We have memory which is interconnected to each of the processor. Instead of 6 memory lanes, we have 8, which is a bit better. And then we have some specific interconnect to GPUs. So we can have 4 GPUs on within a server, 2 for each processor. And the interconnect is using the NVLink generation 2, which is supposed to provide us up to 75 gigabytes per second, which is a lot more better than what we have in Intel system. So I will directly present you the result. So the 2 system I've benchmarked, so the IBM system, and against it, I benchmarked a Dell with 4 socket system. So we have so 4 times 6, 24 memory lanes, which should provide us 512 gigabytes per second of memory bandwidth. That's the theory. In practice, I was able to measure only 160, while for the IBM system, I measured 270 versus 340, which is much closer to what we expect. And when it comes to the interconnect, of course, the speed to the GPU from the CPU to the GPU is it's better today compared to yesterday, but it's far below what we can obtain with the IBM system. So this last figure is the reason why we consider this option. So to summarize quickly the strengths and the weaknesses of the IBM Power, basically, it's a huge bandwidth. That's the reason why we choose it. We found out it was easy to recompile everything because the Power9 is a little Indian architecture and it works, let's say, out of the box. It's open source and I like it. It runs also two of the fastest computers in the world, which are Summit and Sierra. They are both owned by the Department of Energy in the United States, but it ensures that we will have some maintenance on those systems because they will last quite a bit. And maybe the biggest surprise was that it was competitive in price. The weaknesses, because they are, well, the user base, most of you probably you've never touched such systems, so the user base is very small. There's no commercial software available, and the SIMD, the vectorial instruction set, which is integrated into the Power9, which is Altivec, is a bit similar to the SSE second generation from Intel, which is a 128-bit SIMD. We'll see later on that there's some consequences. And basically, directly related to that is that we have less optimized code. So let's see what we are interested in at the ESRF. So I'm in charge of online data analysis. So basically, my work is taking images from the detector and trying to find a way to save them. So in 2015, Mr. Mazui, who's also the author of the Bitshuffle plugin, which is widely used by Dectris, one of the manufacturers of the fastest detector we have here, summarized the need for compression in scientific data. So the compression needs to be unbiased, nearly lossless, and to be useful, it needs to be fast. Fast compression and, more important, fast decompression, much faster than I/O. And to be fast, we need to have it threaded. So we need multi-threaded decompression for performances. And well, maybe one day the HDF5 library will become multi-threaded, and at that time it would be great if the library we have underneath is thread safe, so that there's no race condition or things like that. So we already spoke quite a bit this morning about the compression scheme in the compression pipeline in HDF5. So here I retook the sketch from Andrew Collette in his book Python on HDF5, where we start from a NumPy array which gets sliced into chunks. Those chunks are then, they can be shuffled, compressed before being written to the disk. And for reading data back, we decompress, we unshuffle, we rebuild the chunk, and then we rebuild the NumPy array. What is in green here is the famous HDF5 filter plugin we have discussed longly this morning. And one comment that was made in Andrew's book is that the shuffle filter is very, very fast, actually neglectable compared to the compression time. And we will see that this is not the truth due to, well, the hardware accelerator. So there's an NX, so, well, this is an X-ray image of the Power9 processor, and there's a small part here which is on-chip accelerator. So the Power9 has an gzip accelerator, so industry standard gzip. It can compress up to 16 gigabytes per second of data. The source code is available here. Basically, you do that, you do make, ld preload, blah, blah, run your program, and it works. So I'll show you some benchmarks. Those benchmarks have been done using data coming from an Eiger 4M detector, first generation Eiger. So 1,800 frames, 4 megapixel, 30 gigabyte of raw data. So this data set takes typically 30 seconds, 1 minute to acquire, just to give you an idea. And the data were initially compressed with the first generation of plugin manufactured provided by Dectris, which is the simple LZ4 plugin, and the compression was the compressed data was 5 gigabytes per second, which makes a compression rate of 6 times. It gives you an entry point for what we'll get later. So basically, we take all the frame, we create a new HDF5 with all the frames in it. The chunk size is 1 frame. We pack one after the other. The code is in Python. we use one single thread, and this is the performances we obtained. So I put it in a megabyte per second, and we can see that, well, the Xeon is slightly faster than the Power9 when it comes to software compression. But when you activate the hardware compression engine, of course, the performances are much better. This time, 4 times better compression. Compression, decompression, the ratio are almost the same. An interesting feature is that the compression level, when using the hardware compression engine, is even better than the software compression engine. But as soon as we switch on the byte shuffling, which is implemented as part of the HDF5 library, basically the performances collapse. So basically within the HDF5 filter plugins, we have the compression part, so bzip2, gzip, LZ4, and so on, the Z standard, there are a few others. But the pre-filter stage is also quite important. So we have the shuffle, we have tested that there's a problem at this level, but there's also bit shuffle, which is used by the plugin, which is now used in DEC-trace detectors. There are a few others, like the Delta. And there are issues with building this plugin and shipping them. We have discussed this morning. Then there's the Blosc library. And what is great with Blosc is that it is a meta-compressor that provides you all the pre-filter you need, all the compression engine, and you pick the one you want, you assemble them, and it works. And when you read back, it repicks the proper, rebuilds the path the other way, so that you can retrieve your data. Another great thing with Blosc is that there are SIMD implementation of the different filters, and it will allow us to test some direct conversion of SSC2, so Intel SIMD, into IBM SIMD, which is named Alphabet. So the question remaining is how fast are those filters, and does the implementation matter? That's where we are going. So the first test I did is basically take the plugin from the bit shuffle LZ4 plugin and redid the test. So for the Xeon, we have here the results in compression or decompression. It doesn't matter really which one we take, because the results are really similar. So the basic C code is giving something. 128 bits SIMD is slightly faster. And big surprise, if we go to a 256 SIMD implementation, the performances are less. So this is quite striking. I'm not the only one to notice this. Actually, AVX tends to be quite energy consuming, and the processor have to clock down in order to be able to use those units. So actually, going to too wide SIMD doesn't always help. Well, second things to notice is the compression rate. We went from 6 times to 21 times, which is quite nice. The people managing the storage, the NFS storage, would be really happy if we could get an extra 5 times in storage space. And if we compare now the Power9, so I've limited the Power9 to only 12 cores, while the out of 16 to be on pair. And the Power9 actually is faster when it comes to pure C code, and the SIMD instruction from Intel directly transcompiled by GCC actually brings a little extra, more on the compression side than on the decompression side. So then I went down, just focusing on the filter. So here we are speaking about the shuffle filter. This graph is for the Xeon system. We have the performance here, which correspond to shuffle and unshuffle using C code. And those are the same using 128 bits SIMD and 256 SIMD. Basically, we see that if we use plain C code, we're 4 times slower than using optimized instruction. So one message to the HDF group, this code is available It's available in Blosc, it's available in bitshuffle, well, just take it and put it in your library. You will gain a factor 4. What now if we take the SSC2 code and put it on the Power9? So the performances of C are quite similar to what we have on Xeon, but well, the curve in green and in red are quite similar. The biggest difference maybe is that here above 4 megabyte of data, the performances collapse, and this collapse is related to the fact that actually the cache, the last level of cache L3, which is 19 mega on this computer, is full, and we are coming back on the bandwidth of the memory. The Power9 has much larger cache. Much larger cache means the collapse will occur only later on, so we have more room. Yeah, that's it. If we go to bitshuffle, the figures are a bit different. Here we are at 12 gigabyte per second. Here we are only at 4 gigabyte per second. And well, the SIMD instruction used are much, well, bitshuffle is much more complicated compared to bitshuffle. The conclusions are more or less the same, and the code should definitely be optimized for the Power9, whereas the auto vectorization or the auto translation of SSC2 code doesn't work that well. Yeah, that's it. So now we take optimized shuffle, optimized bitshuffle. You take the hardware compression, you put everything together, and thanks to the Blosc framework, we're able to do some benchmark. And basically, we see that here, using the shuffle filter plus the hardware gzip, we are able to compress around 10 times, 12 times, using 8 threads at a bandwidth of 12 gigabyte per second, which is quite interesting. And for the bitshuffle part, we will need more threads because we will need more computing power to do this bitshuffling. And the best performances are obtained here with 16 threads. Also, 12 gigabyte per second, but a compression rate of something like 8 times. In both cases, the best compression, the best balance was obtained with really moderate compression level, in both cases too. So to conclude on the computer, well, about the Power9 architecture, all our tests worked straight out of the box, just after simple recompilation. We have really been impressed by this. The automatic SSL2 code translation to Altivec works nicely in GCC 8. It's probably not as good as native Altivec code written, so there's room for improvement. Technically speaking, the Power9 win each time. Bandwidth was the important factor. The hardware compression engine works really nicely, and it does the complex job for almost free. And one thing to notice is that Python and other interpreted languages are noticeably slower on the Power9 compared to Xeon system, about twice slower. Sorry. So about the Dell system, well, it had a lot of memory, but the memory bandwidth was only 1/3 of the theoretical value. This computer is indicated by its PCI Express version 3. It turned out also to run much warmer than what we are used to for this kind of servers. And the size of the cache L3 of this computer is really the problem, because most performances are, we would consider suboptimal due to this. And conclusion about the HDF5 compression framework, this has already been asked this morning. Would it be possible to have multi-threading OpenMP for doing compression? Well, the gzip shuffle has been implemented in 2002, and we have the feeling that it was left untouched since then. So it still works, which is great. But SIMD implementation are available everywhere in the nature. Just pick the one you want and bring us a factor 4 in speed we are missing. So many compression features are missing. Bit shuffle is one of them. Many compressors are missing while free to redistribute. It would be great if they could be provided. And the plugin story we already discussed this morning. And what I'd like finally to mention that all tests were done using Python and H5Py, but I doubt the picture would have been much different if the code was written in C or C++. So finally, I'd like to acknowledge Francesc for the help he provided me in, well, basically porting Blosc to Altivec, which, voilà. I'd like to thank my management, and I'd like to thank the big team in IBM who helped us to put the hardware compression. Officially, this is not yet production ready, so we had a beta version of the firmware. And I just got the information today that the version we had will be put in official production and well, soon. So now it's production ready. I'd like to thank you for your attention.
Just a quick question. Have you tested when your compressor is defined with the hardware compression? Did you try on some other system and see how it works? The gzip library still working, I guess.
Yeah, I compressed on one computer, decompressed on the Xeon, and vice versa. And yes, it works, fortunately. Fortunately.
Good. So yes, shuttle code was not touched for a long time, and I'm not sure why it's slowing down. And no one complains. So now first time I hear that complaint.
It was written in the documentation that speed is not important. Anyway.
So we'll take a look. Bit shuffle, as I said, showed it's available, but as you pointed right, it's not one of the features that come, and we'll take a look. Maybe we should include it. About multi-threading, compression is definitely the place where we can include multi-threading. And my question is, I know that there's multi-threaded gzip library, and when it's utility, not library, utility.
Utility, yes.
And my question is, when it compresses, can we use library to compress, or it's really utility that chokes the data in chunks, compress each thread, compress the chunk.
Parallel gzip it's what it does.
So there is no one chunk that is compressed at the end.
What Mazui is doing in his bit shuffle filter, basically he's taking multiple chunks and he's assigning one chunk to each to a different.
We can do it different ways. We can do multi-threading on several chunks. So each thread takes one chunk.
Yeah.
Or it can be several threads working on one chunk.
I wouldn't go that way.
Okay.
I wouldn't go that way.
Okay. Because for that we will need, and I believe Blosc compression, that's what it does. It chokes the chunk of data into multiple pieces,
yes.
And then it stores some catalog with that, how to find the pieces in the big chunk. And that's what holds us, like it's different from what HDFI library is doing, because
you're writing by block.
No, he stores blocks. As I remember, it will be he chokes the chunk of data into pieces, and there is small catalog at page where to find pieces and their sizes. And we considered that option too, but it will be far from that change. But the first thing, we will focus on multiple threads working on multiple chunks. This is something.
Reread the publication from Mazui and his code, which is available.
Okay.
And the job he has done is quite decent, because the performances for reading and writing are pretty good compared to what we have in a. So here we are 3,000 decompression. Here we are 500, so it's quite a nice gain. And what he has done, well, LZ4 is a very fast compressor, not very efficient, but what he has done can be transposed, replacing LZ4 by gzip, because both libraries are thread safe.
Any other questions, comments? You still have that computer?
Sorry?
You still have that computer?
The one on which almost everything has been done, no. We had to give it back. But we have the same. It's just missing the hardware compression engine firmware, which we have somewhere else, but we need to replace the firmware in order to reactivate the feature. But yes, we have, well, actually we have even a lot of them. Nice to play with.
Yeah, I was wondering, is multi-threading compression really that important practice? Because I would assume that typically you're running multiple processes the system, so you're applying cores, or like busy, you really get advantage.
No, we don't. Well, I'm supporting quite a bit scientists who are trying to write code. So Python has a nasty feature, which is named the GIL. Most of you probably are aware of, that prevents multi-threaded code to run effectively in a multi-threaded way. So many scientists are trying to solve the issue with the GIL using thread, basically using just a multi-threaded reading library like the bitshuffle LZ4 as it is implemented today, solves, let's say, 90 or 95% of their needs. So for us, supporting them, it's great. Basically, if they can write serial code, read data, process data, save data, the reading was the bottleneck. If the bottleneck of reading disappears just by using the plugin that parallelize the stuff, it's wonderful.
One comment about the multi-threaded compression. So we had one project where we were like had a task of like writing basically like a saturated gigabit link into a HTML file again, and of course we said, well, we use compression because it's like less work to write on the disk because it also compressed quite well. But the problem was that we basically had just one core doing the compression, and then everyone else was just like waiting until the compression was done. It was too slow, and finally we said, okay, well, we don't compress because our only option was actually use the standard compression algorithms, and so we could not compress, and we just had to write everything on disk. So I think, of course, I mean, it's like let's say like a desktop computing thing, and as we're like a small third-party target are in that range, but I mean, having the compression being done in a multi-threaded way, which I think should be not difficult because I mean, you have chunk anyway, which you need to compress. I mean, that would be a big game already, I think. But I think this is what people are doing in some of the suppliers. This is what Decris is doing, multi-threaded compression.
I don't know how they are doing it internally. I know that the computers they are using for doing that is a real beast. And
yeah, so we'd like to have it, do it in a common way.
Yeah.
But any other comments? Or?
They're using their chunk like the computers.
I think so. I think in order to be able to parallelize, Decris is using a direct chunk write. Yes.
Yes, so they compress data that they use, but they don't not use multi-thread because you should have one that's covered. They compress data and write direct.
Yeah, but each frame is compressed separately. There are some Lima gurus around them. Okay.
But Lima is using direct channel write and they are using multi-thread, so they do it the compression. It was one of the comments in my presentation. It was that everybody ends up doing that. Why that is not in the area?
Yeah, would be great.
That's what would be easy to add. Several threads working each one on each one chunk. Yes, that is something we planning to do. It's relatively easy.
Yeah, and also, I don't know if it was in this project that we got good help from the
HDF group now for some problems with the library on Power9?
I'm just raising
He's on that.
we don't see 128-bit 14 now.
There was an issue with the floating point on Power9.
Yeah, there was a, well, actually the bug was in H5Pi. We've been struggling because initially we couldn't do this test because there was a bug in the internal representation of float 128, which was blocking the well, basically we couldn't read the data.
Right, because it's just local data.
No, it was HDF5. It was HDF5 data. Those were data from the next generation of detector.
No, but HDF5 doesn't support 128-bit floating point, so I don't know what you guys mean.
There's a way to create arbitrary floating point data types. And
It's true, but it's not. You need to have your own conversion function, otherwise you will not be able. It's not workable. So whatever is done now,
there's a way of creating a float that you can tell it what the sizes are, and then what type of extra type of float.
how can you convert it to 32-bit or how you need it on that level?
You can do that.
No, we don't.
We have to do
We have I have a issue that will support 128-bit because Power9 now some of the platforms we have to support and some we won't, but they don't have this problem. No one uses it. We will support.
And the other problem we have with the quads in the H5Pi is that NumPy lies about how big they are. So you get the types, you get how big they are, and then you correct the types to be correct, and then we can essentially round trip.
And then with the Power9, there's a bit peculiarity on float 128 because actually the Power generation up to the Power9 used a certain representation which was non-standard. And since Power9 we have the IEEE 754, which is normalized, which is great, but the Power9 can be used in one mode or another. And when you get the data, you don't know in which mode they were actually saved. Which
right. So we will be implementing that standard on Power9. There should be a function that converts memory representation because you might have compiler switch, right?
Yes, there's a compiler switch.
We had similar issue when we supported the DNS system, and we agreed at that time that we were supporting only IEEE. So but we may have so the library will be compiled with IEEE.
The IEEE mode was working okay. It's the long double mode which was crashing things.
Right.
Okay. So just to say, I mean, is anyone else using Power9?
No.
Maybe next time. Yeah.
You can get them on Travis now.
Okay. Okay.
Really?
Yeah.
Great.
But that's why there's a bug in it. That's why I was asking you to start that machine.
We can play with it. We have 2 days.
Okay. Thanks, Jerome. So the next talk is Thomas Caswell. Very glad to have. We've got a whole team of people from H5Pi here. I suppose I could ask who's not using H5Pi and get very few hands, maybe. But no, this is obviously, as Mike said this morning, this is one of the killer applications that's helped spread the use of HDF5. So I'm looking forward to his talk. And this is HDF5. Okay. And this, for those of you who are not coming tomorrow, the next day, there'll be a code camp on H5Pi, where people will be working on issues together. So we also got James Tucknell from Australia here, and we're just waiting for Thomas Kluber, and then with all of you, probably be, I don't know how many issues you're planning to fix tomorrow, but quite a few. Okay, cool.
Start at the beginning. All right. Turn this on. Is it on? Yes. Okay. So as I'm speaking on behalf of H5Pi, James, as we mentioned, James is already here.
Literally just landed from Australia, so maybe don't ask me too many hard questions today. Right. So, with the history of H5Pi, it was started in 2008 by Andrew Golette when he was, I think, a grad student. Basically, it's a size-on wrapping of issue 5. Andrew has moved on to other things and is now maintained by the community. So James, myself, Tom Soiber, Matthew Skokas has come back recently. Actually, there's 3 or 4 other people in this room who have commits in it. So everything's on GitHub. Second link is the docs. And it turns out we're the 129th most downloaded package on PyPI. And here. Well, those numbers are kind of absurdly high because a lot. On the bright side, everyone has started using these integration. On the downside, that means our download numbers are completely bogus because it's mostly TI jobs. And I think the absolute number of user base has exploded in the last couple of years because Keras and TensorFlow use H5Pi for their model writing. So that also leads to a lot of interesting MPI bugs reports there. So the basic philosophy of H5Pi, unlike PyTables, is that it's a very direct wrapping of libh5's API to Python with just enough of the hard edges smoothed off to make it feel Pythonic. And so it's much less opinionated about what you want to use it for than PyTables, but it also means that the big performance gains PyTables gets when you use it for the things PyTables does, we don't provide those out of the box. You have to do that work yourself. And again, I think most of this room is familiar with H5Pi and Python, so this next section will hopefully go quickly. But the core analogies are the group and the file are basically a dictionary that you can use that item to slice into however you need. And then the data sets are basically our model does not by-race. So can you read that? Okay. So this is the whole world of writing a file. We put listen, we automatically upconvert as needed. You can put numpy arrays, those are happy. If you put slashes in the names of the data set, it will automatically create the groups. And if you need access to all the nonce, there is a create data set method that gives you this, pass through to almost everything in the data set creation. I can remember the property list. If you want to get data back out, you do this. You have usable records on them, so you show the file. If you do select square bracket on the files and groups, you get to dig in. If you go list line, you get to the contents. And if you access the data set, it will give you the record, but at that point, we haven't actually pulled it up from disk yet. It's still lazy at that point, which is important if you're looking at these like 5 terabyte data sets that we were being shown yesterday. Then to get the data out, you use NumPy style slicing. So colon gets you everything. You can do range slicing. You can do sharded slicing across multiple dimensions, just like NumPy. In fact, I think one of our tests is if you take a NumPy array and do the same slicing on it and do the same thing on the data set, you get the same answer. So we're relatively sure we're catching the majority of the NumPy API. And you can pass in lists of integers. You can also do arrays and pools, and I think just scalars to pull out single elements. And then to get the groups, you can either do repeated square bracket slicing to dig in, or if you put slashes in, we expand that and do what you expect us to do. And for good hygiene, it's always close your files. So you noticed earlier I was using a context manager to do that, but make sure it gets closed at the end of the block. Make sure you can't forget. But it was nice to check these out one at a time, so we showed it that way. So I'm going to go through the last 3 versions of H5Pi. Because we are just for the most part, mirroring H5's API, which has been, which is fortunately stable. There hasn't been a lot on our side, right? It's not so in 2.8, we exposed some low-level stuff to registry and file drivers, and made it, exposed more of the knobs to the API, so you can ask it to track the object creation order. So if you want to iterate over your slated book on that and put it. So in 2.9, we had two really big features that are, and a number of other ones. So we got I think in 2.6, we exposed the low-level API for creating virtual data sets, but it was, you basically had to write C code in Python, which, while technically possible, isn't particularly fun. In 2.9, we got a high-level API for that. We got, using actually the file writing, or the virtual file driver feature from 2.8, we got someone wrote us a virtual file driver that takes Python file-like objects. So you don't have to pass the file name to HTML. You can do whatever you want on the Python side. So it's all HTML. Controlling more of the API going down to the chunk cache. NumPy has its zeros like, and now the data set likes you to create a virtual clone, and just more creation order tracking. And we always fix a lot of small bugs every release. So going through the two big features from 2.9, the virtual data sets, I think, for the lights of people in the room, is a good story of collaboration. The first work was done by Aaron Parsons at Diamond. I then did a fair amount of work on that pull request and tweaked a little bit on SLS2. And then the work was finally finished across the finish line by Thomas Weber, who's from European XDOM. So how this works, we've heard virtual data set a lot the last couple of days. So what this lets you do is let you create a data set that points to data sets in other files or subsections of those data sets of files. And then when the user reads that data set, they don't know which file this came from. It doesn't look like a normal data set. So first we just create 4 HTML5 files that have a 1 by 100 data set. And then we declare we have a virtual layout, which is 4 by 100. In that layout, we put the virtual sources, which point to the file name and the data set within that file to pull, and how big that data set is going to be. And then create a virtual data set is what turns the current time to 5 to set that up internally. And just for comparison, I've created a second data, a normal data set for comparison. Oops. And here, if we open up that file and build map, you can see that the first block here is the virtual data set. The second block is the normal one. And from the point of view of the client API, they're completely identical. The other big feature in 2.9 is being able to pass file likes into file. This is actually I think this was Andre's first pull request into H5 file was this massive block of Cython. And if you want to commit bit, if you give us something of this scale in the first pull request, you commit bit. So this means that anything from using Python Open or byte.io objects can be passed directly in. And this lets you do cool things like having a completely in-memory HTML5 file that you can use H5 to work on. So this is just creating a small thing, which is one array in it. If we scroll back and just peek at this, we can see the first couple bytes of an H5 file. And if we hand this thing back into H5 into the file creator, we can read it out and get that data back. I think this is particularly powerful if you have to run, say, a web server that needs to serve HDF5 files to someone. You might not be storing that as a native HDF5 file, like in the database, or they want to chip off some small section of an HDF5 file. You don't want to ship them the full thing, you want to ship them the hyperslab they want. You can now generate the HDF5 file entirely in memory and just serve it to them and never bother writing it to your local disk, which can get you good performance gains. You can also use this as an IPC protocol, right? If you're interested in passing complex structured data between processes, instead of inventing some complicated thing, you can just use HDF5 headers. And just as a further example that this really is doing what we said is, we can take that buffer, write it out to a discount file called .h5, and then we can either open it using HDF5's normal internal file mechanism, or if we use Python's open to open this thing in binary mode, we can then pass that new file handle into the file and still get the data back out. Not sure why that ended up there. All right, so H5Py 2.10, I think we did it last week. So this is brand new. This includes so PyTables will write out binary fields as binary bit fields. We now have better support for reading those. We've deprecated the implicit file mode, which I'll explain that in the next slide. There's better tab completion out of the box in Python. Some helpers. We've greatly improved how we handle special types. So like virtual variable length strings, variable length arrays, that sort of thing. So hopefully that just makes people's lives better. And we've also exposed some more low-level APIs that they don't have high-level viewers yet, but if you need them, you can get them. Right. So a very early design decision was the default mode if you don't tell file what mode to open is a kind of hybrid that first tries to open the file append. If that fails, opens it I think exclusive. And so it's convenient because if you just want to write something, you just write the file. But it means that by default, users are opening file to rewrite, which is not something you want people to opt. You don't want people to accidentally open the critical data set. They think read only, and then accidentally type something that it's their thesis from the data. But we didn't want to just change this in one step because now, like, there are some people who are almost relying on that feature. So we deprecated not passing it in our warning. You get this lovely warning here. If you're seeing this warning and don't want it, there's on the global config object, you can set the default file mode. If you set it to R, that's what it will be going forward. Or if you need to get the old one, you can set it to, I don't remember the other values. You set it definitely set it to A or X. And you set it none, it goes back to 1. Right. Your scale helper is just if you want to scale in your data sets, you might make that so easier. Right. So our next release is planned to be 3.0. The big changes are going to be changing the default file mode, and we're going to drop support for old versions of Python. Getting ready for the Q10, there's a number of pull requests having to do with how we handle strings, making sure unit code goes through carefully all the way, and controlling the way that we encode date times up and down through HDF5. There's some, hopefully we'll be getting it done in the next couple of days, discussion about how we want to move forward on those. And then we've recently been getting a lot of bug reports related to MPI usage. So hopefully we can, hopefully someone who will be at the code camp is an expert in MPI. You can help us sort out either how we can fix those bugs or make it harder for users to shoot themselves in the foot when they do non-MPI H5 operations in MPI inverters, and then everything breaks. And there's been some requests for better support for, I think what are called fractal data sets, where you're ragged at all of the levels. Like I mentioned before, there's a code camp on Friday. We've got Thursday and Friday. We've got a project on GitHub where we started to collect some issues that we think we want to work on. And we have issues reviewed for work at every level of expertise. From making the docs clear, there's a number of low-hanging performance tuning where if you just understand, one function, make sure the behavior doesn't change, the performance gets better. Bug fixing and triage. There's some discussion making sure that the coming 112 release, we start mirroring the methods from that we want to mirror up, particularly the vol work and the API discussion. So if any of that is interesting to you, please come. And with that, are there any questions?
Questions? How do you divide up your daytime work between real work and H5i and math?
So I guess between so both MATLAB and H5i I use entirely my day job, so I get a fair amount of flexibility to work on those at work, but I'll make something between 10 and 20%, and then a lot of nights and weekends.
Yeah, so basically we don't know. Tom is also maintaining of NX-compressor, which is the most used project. I think science owes you a lot of work. Yes.
Thank you for the great talk. I think you just solved my streaming issue problem.
Yeah,
If the file gets sent to me as a binary blob, I could wrap it into a byte object, and then open it with this, right?
Correct, but you have to, I don't think you can open it while it's coming here. So you have to wait for the whole thing.
Yeah. Thank you very much. I'm so happy that.
Correct. I want to line walking away. I had another question. Would it be possible to add, because we discussed this a bit, the continuous integration link with the H5 library?
Oh yes, that's actually one of the issues tagged for the project is to you mean to push up to your dashboard. If you can tell us how to do that, yes. Because the other thing about it is you also want to get a build where we pull either your snapshots or your develop branch and run on that to make sure that we still work on your bleeding edge.
So just a question about maybe there's another way, but now when we want to see the same buffer in a file using different shapes, we have to create a different data set to the same file we are in. Is there another cleaner way of doing that?
You want to reshape something?
Yes, without duplicating the data. For instance, you are saving all your data as all your images in a flat disk, and you would like to see that as a 3D stack and provide the dimensions. You do not want to duplicate that, so that acquisition can write it as data coming, and the visualization could adapt that to be seen in a different way without duplicating the data. At this moment, we can do that, creating a virtual data set, pointing, in fact, to the same file, and we do not find a late key. So if there would be another way, I have to say that.
So, sorry, I'm thinking. I think so. We already have an as type property that acts as a context manager that gives you a view into the data set where we do the conversion magically on the way out when you access it. It seems plausible that H5 could have a reshape method on the data sets that would then let you slice on it against those new dimensions and would then do that reshaping into when you get to NumPy space. But oh yeah, you can definitely do that with sprite tricks. If it's contiguous. So maybe with limitations. But that does seem like something interesting. That we should work on in the next couple days.
Yes. Can you just put
So you talked about the improvement for dead time objects in H5.5 3.0. So is there already something in current version of H5.5 for dead time objects? And if there is, what is the link with NumPy dead time 64 objects?
So currently there is no automatic link. Like if you give H5.5 dead time 64 object, it says I give up. I would need to do this. You can manually mark on that thing somehow that it is dead time 64, and then cast it in 64 and write it down. And then your application code has to know on the way back out to say, okay, I'm going to open this data set and read it out at 64, and I know I have to cast it back to daytime 64. What we were discussing is a way to register either per write, with the context manager, or globally, a way to say when you see daytime 64, we'll put a mark on it that we understand, and then do that whole cycle for you, so it ends up being transparent. But the concern is how do you do that in a way that you're sure you're not going to stomp on the user's anything the user wrote, right? Because if you grab the attribute like I am at datetime, it's entirely possible a user has grabbed I'm at datetime for their own purposes, and either you'll break or stomp on there and like break them in very surprising ways downstream. So I think where we got hung up was how automatic should it be, and how much do we want to force you to opt in? Is that?
Yeah, that's right. Thank you.
any more? Ample time in the next 2 days. But okay, I want to thank Thomas again. Thank you.